We'll start here. Alrighty, welcome. This is Team AJ3. We have Abby, myself, Jen, and Jillian. We all work together to examine some hospital utilization trends over the COVID-19 pandemic timeline. We're going to give you a brief introduction and background into the data set that we worked with and how we put this project together. The data set itself is it's from the California Department of Healthcare Access and Information. It combines a couple different features. It's hospital setting, its date, health category, hospital system, facility name, and then frequency count of how many times a patient visited a hospital and had the issue of a specific health category. This data spans from 2018 all the way to 2022, so before, during, and after COVID. It's extremely important to utilize this data to identify and understand some different trends in hospital resource usage, specifically prior to a major event like the pandemic, as well as after the pandemic, to see really, at least in a state like California that has such a widespread variation between rural and highly densely populated areas, and how their healthcare systems have rebounded from COVID or lack thereof. It can be easily applied. This analysis of this historical data can easily help drive some of that data, that planning and policy development for future healthcare emergencies. So that's the background behind our data. It was a CSV file originally. It has over 80,000 rows of data. Extremely useful and highly dense data set.
Thanks, Jackson. Yeah, so now I will go into our exploratory data analysis. So to get started, we imported essential libraries like NumPy and Pandas for data handling and Matplot for lib for visualization. Our first step was to get the data cleaned up and organized, which included aggregating the data by month and by category to ultimately help smooth out any bumps or inconsistencies. And then we also checked for dealing with any missing values, duplicates, or outliers to make sure our analysis would be accurate and reliable. And so then for the identification of missing values and uniqueness, so we calculated how many missing values were in each column and how many unique values each column had. Most columns were very complete with a few missing values, except for the system column, which had more missing data. And then this summary step really just helped us know the quality and consistency of our data set before we really dove in and moved forward. And so then going into our data set exploration, we wanted to understand the full landscape of the data before narrowing our focus. So we printed out all the unique hospital settings and categories, as you can see below. For example, settings included ambulatory surgery, emergency department, and inpatient discharges. Categories covered everything from anxiety and diabetes to respiratory arrest and failure and stroke. This step was making sure we were aware of all the possible types of encounters before even diving further into the data. So then our data frame creation. So we created and aggregated a data frame that totals all the encounters, encounter counts by category and by month. This let us start exploring which categories had the highest average encounter counts, which ones were more volatile, and how these numbers changed over time. So for example, hypertension and diabetes showed some of the higher mean encounter counts, while some categories like COVID and homelessness had more volatility month to month. This summary gave us a clear sense of the bigger patterns and surprises that might be in the data, and which really set us up for a more focused analysis, which we will get into.
Thanks, Jillian. Moving on to our data visualizations. Um, we first started by setting up our plotting environment, and we ensured that there was one chart for each unique health category, such as anxiety, asthma, cancer. We then arranged these charts into a subplot grid displaying four charts per row. The share x equals true argument was crucial in this setup, and it made sure that all the charts shared the same x-axis, which greatly simplifies comparing trends across different categories over time. We also used the axis flatten attribute to transform the multi-dimensional array of axes into a one-dimensional array, which allowed us to manage each subplot efficiently using a single loop. Our loop iterated through each column in our aggregated data frame, each column representing a different health category. And for each category, we performed a number of actions, which included plotting the monthly utilization count, setting the title to correspond to category names, rotating the x-axis for improved readability, and labeling the y-axis is count to clearly indicate the utilization. And after plotting all these categories, a line of code removed any unused subplots to prevent any blanks appearing in our final grid. And then some insights we can derive from this. By observing these plots, we can quickly identify trends for each category over time. For instance, we can clearly see the spike for COVID in early 2020 and how many of the other categories saw significant decreases at the same point in time. However, we did want to point out there are some categories that didn't follow this trend exactly. One being homelessness, which sort of remained relatively stable throughout the pandemic. And the utilization counts for cardiac arrest, respiratory failure, and pneumonia all increased sort of during this time. And this sort of approach just sort of allowed us to observe everything in one like comprehensive, powerful view.
Yeah, thanks, Abby. And just to go off what Abby was talking about, specifically really important to see some of these trends, like you see with pneumonia, sepsis, and the respiratory arrest and failure, and how those really coincide with an increase in COVID, as a lot of those were direct factors that and health issues that COVID typically cause. Well, typically, when you saw the reporting cases for deaths by COVID, in reality, yes, the deaths were caused by COVID, but typically that comes into play because things like sepsis and respiratory arrest and failure were what actually caused that cause of death. And knowing things from that first plot, we factored in a little bit more of wanting to see the setting of these different categories and where these different health crisis categories were being treated. And so that's why we got into these different settings. And there's ambulatory surgery, emergency department, inpatient discharges. And here's a short synopsis of so we can understand what each of these are. Ambulatory surgery is going to it refers to some surgical procedures they're performed in an outpatient setting. Think tonsils removed, things like that. Quick knee surgeries, things that don't require an overnight stay in a hospital and discharge in less than 24 hours. Emergency department, anything and everything. Refers to a designated area within a hospital. So they're tracking the amount of people that are coming in through into the hospital via emergency department. Open 24/7 operations, typically treated right there within the emergency department. Inpatient discharges is going to refer to a patient who goes in the hospital, they receive medical care, and they have to stay for at least over 24 hours, a minimum of one night for when they're being treated. So as you can see, similar to what Abby just talked about and was kind of talking through some of that code and how we designed this, we had to do a little bit of tinkering to some degree because we wanted to stack these and kind of really get an idea of an overlay view. And that's why that stack plot comes into play there as well. So as you can see here, here's our output. We've got total encounters by the different settings. So what you will see, and it's nice to see that our data is really tracking that the spikes that we saw on those last charts that we just referenced that Abby went over are consistent with what we're seeing here. Again, you can go and see that certain things that are going to be really, really important or really life-threatening, excuse me, are going to be treated in those inpatient discharges. If you go into cardiac arrest, they're going to want you to stay in the hospital for more than 24 hours, and as well as a really high amount in those emergency department there. The people that are going through the cardiac arrest issues are going to be treated in the emergency department rather than the ambulatory surgery route. And you can get in here specifically as well. Really shows that where when we diagnosed, when you were taking care of people with COVID and trying to really save lives, they weren't going through the ambulatory surgery route. They're going to be in the emergency department. They're going to be kept over a certain amount of time. And it's also interesting to see as well, really reflective of some of that return to data, like you see things in depression. And ideally, that variance that you might see with like ambulatory surgery is going to be a lot smaller. It's going to be more that outpatient setting. You're going to see there's going to be less variance in terms of how those people are being treated as well. Again, seeing some more highlights here of scenarios where they're not going to treat you in an ambulatory surgery scenario. Pneumonia is going to be you're going to have to stay in the hospital for a certain amount of time for that, as well as respiratory arrest and failure. Same concept with sepsis. And this is really nice to see this is reflected in our data. It shows our data sets being sorted. We're sorting it in a really appropriate way.
And we also created an alternate visualization of category data by date, this time using box plots to offer a different perspective. So first here, we grouped our data to calculate the total monthly utilization for each specific category. And this helped give us a more consolidated view of how often patients are visiting the hospital for each condition in a given month. And we then gathered a sorted list of unique categories. And this was to ensure that our box plots are displayed consistently, making them easier to compare to one another. And then using list comprehension, we created a list of arrays, and each array contains the monthly encounter counts for specific categories. Some key parameters we set up to sort of optimize this visualization was setting the fig size to make the plot wider and easier to read, especially when we have, many categories that we're trying to display here. And we assign names using labels and suppress the plotting of outlier points by setting show flyers equal to false in our code, which leads to just a cleaner visualization overall. We also rotated the x-axis labels and used a tight layout to adjust the plot and prevent the charts from overlapping with one another. And by looking at this visualization, we can quickly compare categories, and we see things like hypertension and diabetes have consistently higher utilization counts compared to like cardiovascular disease or homelessness have lower counts there. And then the different heights of the boxes give us an idea of the variability and spread. So for a taller box suggests, a wider range, whereas shorter, there's a lot less variability. And this just sort of helps give a summary of the central tendency and spread of utilization across our data in these different health categories.
Okay, so now for the fun stuff, I'm going to talk us through our machine learning model. So some definitions to start. We're going to be talking a lot about SMAP, which is the symmetric mean absolute percent error, which is a metric used to measure the accuracy of the forecast, especially when we're dealing with time series predictions. A time series forecast is the process of using past data points collected over a period of time to predict future values. And then the type of regression that we're going to be using is a random forest regression, which is a type of ensemble learning algorithm that predicts continuous values. It works by creating multiple different decision trees that are trained on different features. And then the final prediction is an average of all of those predictions. So you can see a good depiction of that here.
So then going into our model, our big picture was to forecast the monthly hospital utilization counts by category within the emergency department. And throughout this project, we explored a lot of different settings, and we settled on the emergency department because obviously that's the most pressing, the most crucial department. And if planners can accurately anticipate capacity and resources, it could possibly be saving lives. So for this first section of code, we're just mapping everything out, and we're going to be speaking to kind of our evaluation toolkit. So our MAE, RMSE, MAP, SMAP, and normalized mean MAE. These are all different metrics that we're going to be using to train our model. And then the next section of code to develop the development training model, it's essentially going to be looping through each unique combination of category and setting. It's preparing the features for modeling through these specified time periods, and then it's going to be evaluating them based on this criteria. Something I wanted to point out here was the if statement with a length function in the middle. It's something we talked a lot about in class, so it was pretty cool to get it to see in use in our project. And so then the last line there at the bottom, you can see that we're going to convert these results into a data frame so that we can use them for filtering, sorting, and exporting. So that leads us into our actual modeling. And we were pretty pleased with the models that this turned out. I think they were pretty cool to dissect and talk about. And pretty much we're going to show 5 different models that are all based on the SMAP. This allows us to judge the trend tracking quality of these models compared to what actually occurred. So as you can see, the blue line is what has happened in the past, the data that we're basing our predictions off of. The yellow line, or orange, is going to be showing what actually ended up happening, and then the green is what our model is forecasting. And so that looks pretty similar to me. The SMAP is 2.3, and these top 3 models, which are stroke, sepsis, and non-psychotic disorders, you can see they all have a below 2.7, which is pretty dang good. And we're also able to narrow this down as we went, which is good. And then we also wanted to highlight the sepsis model because if you don't know what sepsis is, it's a life-threatening condition that occurs when the body's response to an infection damages its own tissues and organs. It's a very life-threatening disease, so the ability to accurately predict this would be huge. And having a 2.3% error, we were pretty proud of. And so then moving on to the last section, we're going to take a look at the top 10 forecasted models for the emergency department. And these are all going to be ranked by normalized MAE, which is a metric that helps us understand how accurately they're being predicted. So as you can see here, the top 3 are the same: stroke, sepsis, non-psychotic disorders, and then followed by cardiac arrest and cancer. I just want to highlight those 5 because, once again, those are all very important and oftentimes life-threatening conditions. So we thought it was pretty cool to be able to look at all these different metrics for each of the categories and be able to compare them.
Absolutely. And then get into our discussion and conclusion. Going to go over a little bit uniqueness of why our study's a little bit on its own. There's a lot of data analyzed in our notebook. It reflects a strong focus on like hospital utilization before, during, and after the pandemic. It's a little pretty fairly unique because a lot of data that's been analyzed is either just afterwards, just before, or just during COVID. It's also unique because we're able to really work with some specific health categories, which doesn't seem to be as common. And we've even seen some financial effects, reasons like that in a lot of studies. Obviously, we didn't have that, but we like to think that our data, when paired with financial data together, could really provide some really valuable insight. And you can do a lot of queries with the CDC, the NCHS, looking at a lot of this data of, all right, cancer occurs this often in this location, things along that side of lines. But in particular, really important that we're able to really compile a lot of this data and examine it all at once. You can look at patient transfers again during the COVID-19 pandemic. That's something that's not too hard to find, but again, it doesn't really capture that full scope of before, during, and after. There's also one of the closest studies that was able to locate was some things that were focusing on before, during, and after the COVID-19 pandemic, but it was really only chronic patients, and that's a very loose term and can be hard to measure. So we're really glad to work with a really solid database that provided us a really broad and a wide breadth of information.
Yeah, thanks, Jackson. And then just to wrap everything up, the general consensus of the industry was that the hospital utilization had not largely returned to pre-COVID levels as of the end of 2022, and our findings supported that. Our data was reflective of national trends and also gave us insight into health disease categories, and were mostly in which were most frequently treated across the U.S. We used a modular random forest forecasting framework that Jen had previously mentioned, and this provided actionable 6-month predictions, which can support proactive planning for the hospitals. And the results showed that structured, timely data is essential, not just for understanding what's happening now, but for building predictive models to guide resource allocation and staffing. So going forward, future work should focus on integrating additional variables and optimizing model parameters to expand the model's forecasting power and real-world impact. And then here are our references.
So, yeah,
And
yeah,
you want to add anything?
just to echo what Team Yellow said, the example we saw in class. It's been an extremely beneficial class, Professor Hashimi, and we thank you.
Yeah, thank you so much.